time this morning. I appreciate it. My name is Steve Hetzel. I'm here representing Crunchy Data, and I'm coming to you from Boulder, Colorado. So I think I've got the distinction of being the furthest travel to be here. So I appreciate your time. What I'm going to speak about is essentially Kubernetes, but then how we use that for Postgres, and how do we do on-demand streaming replication. So as we get into it, before I get into the details, a quick question so I understand the audience. How many of you have used Kubernetes previously? Okay, about 50%. How many are using it currently in production? All right, that's what we need to see. What about HELM? Are you guys using HELM at all for package management? Fantastic, okay. And Postgres, do we have Postgres users in the house? All right, that's what I love to see, so fantastic. So, there's kind of this misconceived notion that you should deploy a database in a container, and there's a lot of ideas about, containers are ephemeral in nature, and they're not performant. And so, why would we deploy Postgres in a container? Well, a lot of that comes with it's portable. I mean, you can literally deploy that bare metal, different cloud providers in-house. You can move that around as needed. It's consistent, it's flexible, it can scale. It's got a lot of advantages. So while you would deploy a multi-terabit data warehouse, possibly in a container, for transactional data, for on-demand services for platforms, it really does make a lot of sense. So in this particular use case, one of the things I wanted to focus on is most of the solutions that are out there, the vanilla Postgres images, Patroni, and some of those other things, started out as homogeneous in nature. They were meant for one data center only. But as those solutions have grown, we had to think about disaster recovery, business continuity, and horizontal scaling. So how do we automate that, and how do we have containers go across different environments and do that in an automated fashion? So I'm going to kind of skim through these a little bit more quickly, since most of the audience has some Kubernetes background. But essentially, a container is just an isolated process. It's standalone, can be deployed across different environments. I'm sure you're all familiar with the workflow. You build a Docker image, you push it to a repo, you pull it and deploy it to a Kubernetes cluster. Kubernetes itself, obviously, is that orchestration that provides the scaling, the services, the service discovery, and a lot of the different nature around the individual containers, because we wouldn't want to be managing hundreds of individual containers by themselves. So yeah, Kubernetes, so it does the node scheduling, recovers automatically from failure, can provide basic monitoring and logging. And with that workflow, essentially, you're deploying a container via the API server to the cluster. It will get scheduled to one or more nodes. And then the pod is attached to a persistent volume or a disk, which could be Gluster, could be EBS, and essentially provides that ability to recover from failure and provides that consistency. One moment here. My laptop seems so frozen. I apologize. Okay. But essentially, as developers, all you really need to care about is talking to the API and deploying your container cluster. So for Helm, this is where things start to get a little bit more interesting. When you're working with that Helm, you end up deploying many different YAML files individually. So using kubectl apply, kubectl create, and if you've got 15 services, a load balancer, a database, and all these different things, you're still deploying all those pieces individually. But with Helm, it allows you to actually package that up into an atomic state, such that you can say Helm install, Helm deploy, and it'll actually deploy all those services that will either be deployed, rolled back, upgrade, etc., and you can upgrade in place. So think of it like Yum for Kubernetes. It essentially allows you to have an entire framework around those YAML files rather than deploying those each individually. And I'll get into that with a demo a little bit later. That's obviously a lot more interesting than slides. But essentially, this is what Helm is. It's a way of wrapping up all these different YAML files together into one package. So for those that don't have Kubernetes background, I like to describe it like this. I described it to my son. My son's a huge Lego freak. And when I was trying to describe Kubernetes, he's like, what is this? What does this mean? I think about it this way. Your individual Lego brick, those are your building pieces. Those are your blocks, your containers, your load balancers, your databases, etc. Persistent volume secrets. And as you put those together, now you've got a pod. A pod is the smallest atomic unit within Kubernetes, and it essentially is meant to serve a specific function or specific service. But once you put that together into a platform, this is where Kubernetes really starts to shine, because you're putting all those different pieces together into one way where they're all actually working together. So what does this mean for Postgres? So Postgres, when you think about it, as compared to Legos, before it was building something out of clay. You could build a platform, but you're having to go out and shape everything individually every single time. So you think about how long does it take to provision a virtual machine? How long does it take via Ansible to install Postgres and configure it and everything like that? That can often be multi-hour, multi-day process depending on your enterprise. Whereas when you've got a built-in Docker image, and when you can deploy that with Helm, we can install a new database in a matter of 10 to 15 seconds. And then as far as a standalone database, with replication, as fast as your network and your storage will allow, you can deploy those streaming replicas as quickly as possible for both disaster recovery, horizontal scaling, etc. They've also found that in many cases, databases perform better in a container environment because they have less overhead and less individual pieces for them to consume. So here, I'm representing my company called Crunchy Data. We're based out of the United States. We're a relatively small group, but we have a pretty large impact on the Postgres community. We've got several core committers on our executive staff as well as our technical team. We provide primarily, we are a Postgres company. So we provide support for Postgres in both traditional bare metal and VM environments. We also have the Crunchy Container Suite, and I'll get to that in just a second, but essentially provides an entire tool suite for managing Postgres and Docker, Kubernetes, OpenShift, etc. We have our individual webpage as well as GitHub. I encourage you all to stop by and take a look to see what is there for you. This is an example of what the Crunchy Container Suite can do for you. We've got everything from Grafana, pgadmin, pgpool, pgbadger, essentially any Postgres tool that you can think of. We've wrapped that with Docker containers, but then also made that available for Kubernetes and OpenShift. So essentially, you can basically take these pieces individually, or you can build an entire platform with it. It just really depends on what your individual use case is. All right, well, let's get into the demo. I think that'll probably be a little bit more interesting. All right, so we've got just a couple of windows up here, and let me go ahead and clear that out. So in this case, what I've already done is I've got a Kubernetes cluster that I've deployed to Google Cloud in this instance. So you'll see I'll bring up the nodes. There's a little bit of latency on the network, so I apologize for that. But in this case, we have a 3-node Kubernetes cluster deployed to Europe West 3 up in Frankfurt. And in this case, we have just one namespace, or we have 2 namespaces at this time. But in all right, so for the sake of this demo, is that too small? Can everybody see that okay? Okay, perfect. So what I've done is, in the demo namespace, obviously we've got our system things running fluentd and heapster and DNS and all those other things, but in this case, I have a demo namespace where I've deployed a primary standalone database. So for example, this might be a transactional database. In this case, it's very, very small just for the sake of the demo, but it could be anywhere from 1 gig to several hundred gig. And then this is going to be in a scenario where we need to do horizontal scaling. So for example, we have increased customer demands, we have a disaster recovery scenario. We want to be able to build a replica on the fly with as little effort as possible.
Steve, while you are doing the demo, you may use that mic, so it's not... Okay, thank you.
Perfect, thank you. Appreciate that. All right. So what we've got here is a pretty typical Kubernetes setup. We've got your chart.yaml, we've got a couple of templates in here, but all the magic really happens within the values.yaml. So this is basically providing the metadata and the specifics that's going to be passed from the Kubernetes chart and through Helm back into Docker. So in this case, we're going to use a standard storage class. You can do everything from SSDs and whatnot. As stated, we're deploying to Europe West 3 up in Frankfurt. And then we get into the specifics. Right now, these are the only values that I've exposed through the values.yaml that gets passed back to the Postgres configuration. But we have the option to expose that entirely or to modify the config directly, and I'll show that in a little while. In this case, we just have a very simple admin user that we're going to call admin. And then in this case, we are going back to this. We're going to have a replica, a read-only replica that we're going to create. We need to point back to the master. So if you'll remember before, it was called the service was called primary. In the demo namespace, it's a service in our local cluster. So what I'm going to do is I'm going to go ahead and just stand up a replica really quick, and then we'll watch the logs as we go. So in this case, we're saying helm install from the local directory. We're going to name it replica, and instead of the test namespace that I used earlier to prepare for this, we're going to go ahead and use demo. And we're going to watch the output here. So we'll see that we have a replica. It was last deployed. It's currently in process. We're using stateful sets. We have a secret. In this case, it's an SSH key. We have a config map, which I'll show later. That's literally the Postgres configuration. We've got a service, and then we're watching it's going through the init phase. So we're using Helm init containers to build the streaming replica before the primary container comes up. All right, so now it's into the init phase. If you'll watch the right side here, you can see that we're actually bringing up a brand new Postgres database. We're running initdb, we're setting permissions, we're setting memory, etc. And then also we're creating basic extensions. So we're using things like PostGIS, you could use PG Crypto, you've got a bunch of different options there. And then we're creating basic roles and replicas. And then here you'll see that we have backup data not found, so we're going to run PG-based backup. So we're going to have transaction start points, we're going to actually run PG-based backup, and now, in a matter of just a few seconds, we'll take a look. From Helm, we had just the primary, and now we have the primary and the replica. And if we look at it from the Kubernetes point of view, we've got two different pods as well. We've got the primary and the replica. So let's go ahead and take a look at what the primary is. So that was the primary is the name of the service, but the pod has a zero-based notation. So in this case, I'm using a one-based, a stateful set of one, but we could have as many. We could have 1, we could have 10, we could have 20 copies of that database for different purposes. In this case, we only have a set of 1. So we take a look at the running processes. You'll see we've got Postgres running. And it's in streaming replica mode. You'll see that there's a wall sender process. So the wall is the write-ahead log. That's how the built-in streaming replication for Postgres handles the streaming replication from the primary to the replica. You'll see right now we've got some just very simple databases out there. Aside from your system DBs, I've just got one called foo. It's very simple. And within foo, we've got a simple table called bar. And let me go ahead and bring up on the other window here. We'll take a look at the replica, and we'll show the streaming replication in real time. So we're going to do kubectl exec interactive session. We're going to connect to the replica on the demo namespace, and we're going to just pass bash. That's essentially the equivalent of SSHing into that container. So now you'll see that we have the exact same DBs that we had before, system as well as foo. If I try to create a new one though, my statement earlier never got terminated, so let me go ahead and just rerun that. You'll see that we can't create a database on a replica because this is a read-only replica. So this is in a primary replica or a master-slave relationship rather than active-active or master-master. But let's go ahead and create it on the other side here. We'll run that same command. We're not actually in PSQL this point. Database has been created, and it's also been streamed over to the replica as well. So essentially, if you can imagine this using auto... Wow, that's really noisy. I'm sorry about that. If you can imagine this using auto-scaling groups. So for example, we might have a primary replica, we're running along, we run a huge sale, we're running into Black Friday. We can actually have additional copies of that database be spun up automatically, and it's in a matter of, like I said, as far as the network will allow. In some cases, on a previous project in a previous company, we actually had a production deployment of this. We built at a DR site where we had 75 production databases totaling about 225 terabytes. Using this methodology, we were actually able to build up an entire DR site on the fly. So we've templated out all of this, no manual work. All you have to do is provide the right values to the values.yaml, build the replica on the fly. So you can imagine that with DR, horizontal scaling, etc. Really the sky is the limit. This is a very simple example, but once again, going back to the country container suite, you can build all of that, essentially that entire platform with very little effort. And if we wanted to get back into the specifics of what that actually looks like, we've got the values.yaml here, but then we also, we've got the Docker entry point, and this is where the actual logic takes place. So in this case, we're actually passing, when the first time that it's going to run a init. We're going to create our directories, basic, logic checking permissions, etc. We're going to create some basic extensions. We're going to use PostGIS, AMQP, which allows you to talk to like RabbitMQ through a federated data wrapper within Postgres. But then now, this is the good stuff. So if the type of database is replica, we can deploy this exact same chart as a standalone by merely changing this value here in the values.yaml. We can change it from replica to a standalone. But if we are running a replica, then we're going to say, basically check, do we have a backup label? Does it already exist? If it does, then we're just going to pick up exactly where we left off. So I could delete this replica right now and redeploy. It wouldn't run through this init process because it already has the data in place. It would just reattach to that persistent volume and pick up and go from there. But if we do need to create a replica, then PG-based backup. So essentially we're going to put the configs in place, and then as the super user Postgres, we're going to go and run PG-based backup with the values they passed into the HELM chart, and then that'll go ahead and create the replica from there. Otherwise, we'll just go right into the run phase and start Postgres and go from there. The only real hack that we did with this particular deployment is you'll notice that the last command that we're running is tailing dev null. And so that's really not best practice in the Kubernetes world, but one of the things that we want to do was be able to exec into the container. Suppose we needed to debug on the fly. Suppose we need to change just the log level from, say, info to debug 5 or something along those lines. We want to be able to do that, which requires the Postgres service to be restarted without having to redeploy the container. So you could change the config value and redeploy the container, or you could just debug on the fly, depending on what your system needs were. But ultimately, as I mentioned earlier in the configs, they're all encapsulated in these YAML files. So you'll see that we have your standard Postgres configs are all here, postgresql.conf, and 99% of that is commented out in line, and we just put, we left that so the user can understand what their options are. But this is really all you need to care about here. And you can ignore Adam complaining at me. But essentially, you can set the wall levels, you can set your archive commands. Essentially, any tweaking that you need to do can be set within this YAML file and then redeployed, or you can change it inline by executing into the container. And then the only other thing that we really care about is the host-based authentication rules, or PGHBA. So for this demo, it's set very wide open. You wouldn't do this in production because it's essentially allowing trust authentication for everybody, including, then this runs in order, the last applying last. So you'll see that we're actually allowing replication from all addresses. Once again, you would probably lock that down to a specific IP range or CIDR block, depending on what your needs are. So, I think that is kind of the bulk of the demo and what the configs look like. I'm going to open it up to questions. Sure.
My Postgres DBA used to configure a lot of sysctl configuration, kernel parameters. Okay. How do you configure that on Postgres, on a container? And then another question. Postgres SQL data reside on it seems a physical volume on Google Cloud Engine?
In this case, yes. It is using a persistent disk for Google Cloud, and I can show you what that looks like. In regards to your first one with the kernel parameters, I believe that would all be set through these YAML files as well. But that's actually a great question and something I hadn't considered, so I'll need to look into that. So give me just 1 second here to back out of the container itself. Once again, I apologize for the latency. It's not usually so slow. So in this case, we have two different persistent volume claims. So within Kubernetes, there's the persistent volume claim, which allows the underlying persistent volume to be attached to one or many pods. In this case, we're using a one-to-one relationship. So if we take a look at that actual persistent volume itself, you'll see that based on the annotations in the storage class, yeah, this is an underlying GCE persistent disk with these parameters. And so that could all be set differently depending on which cloud engine you're running on, or if you're running on bare metal. We have examples within the Printer Container Suite of running on NFS and Hostpath, and then we're currently working on a cluster example as well. So that'll be available here fairly shortly. So, thank you. And I will be sure to actually check into your question, and if you want to leave your contact info, I'll be happy to research that and get back to you directly.
Hey guys, I wanted to ask you a couple of questions because you showed before that we had like a master and then you created another master using a stateful set. So you're going to store all the things in the persistent disk you showed before, and you're using a standard storage class, which is fine. And you're using the streaming replica for basically keep containers aligned between each other, and this is clear to me. I just wanted to understand, you didn't show up the service, so you're using a cluster IP for for the other application which is running in the same cluster to get hits. It can be a node port if other, yeah, it can be. And the last question is, when you define a master, you gotta select which of these master is really a master. I mean, like the one which is able to process all the stuff and then stream the replica. Where are you storing all this information? Like, I'm the master, I got the lock, I'm the second master, but I do not have the lock, so I'm in rate only. And how these can be promoted automatically between each other in case of fault of a container. What we were expecting and what we wanted is that if for some reason one of the container, maybe the master container is going to fail because, for example, it's located within a single availability zone, so whatever it's called, the second one should automatically be in the master and spin it up and handle the connection. I just want to see how you guys face this.
Sure, yeah, a lot of questions there, those are all great. So a couple of different options here. So in this case, we are running somewhat standalone. So if we, let me go ahead and put this back. All right, so if we take a look at the particular service that's been created by this, this HELM deployment, you'll see that we are running on a cluster IP right now, and so this is internal to the cluster only. With other production deployments, what we've done is we've actually created a direct connect between the customer's data center in Washington State to Google's Cloud US Central environment, and we're running over node port. So node port essentially allows any IP address that is allowed to see that port to connect to an individual pod, and so that's exposed directly through the service. So it allows essentially an ingress. So you could run a Kubernetes ingress service, or you could run node port, which is a direct connection. So for example, we might have node port 30,200 might point to the primary replica, or the primary database. 30,201 might point to the replica only. And so essentially allows you to speak to an individual service or an individual pod rather than trying to navigate or connect and then find your service from there. So in regards to automatic failover, so this is not currently set up for automatic failover. Some enterprises like auto failover, some prefer to manually handle that due to flapping issues or whatnot. So in this case, you would probably execute failover by using a trigger file or using pgcuttle promote, standard as you would with any DBA tool. We have a tool within Crunchy called Crunchy Watch, which is actually designed to watch the primary database or the master database. And in case that it actually sees a failure, it actually kill that pod and then promote the other to the primary. And then as far as your question in regards to knowing which is the primary, which is the replica, that's all handled primarily through the use of selectors and labels. So if we take a look at kubectl, let's go ahead and describe the service. If I could type that correctly. All right, so in this case, we've described the service, and you can see this in the demo namespace, and we have the application called primary. And then we also have a selector called primary. So in the case that we wanted to do auto failover, CrunchyWatch essentially would promote the replica into the master status, but then it would also remove this particular selector from this service and then apply that to the other service. So essentially, you would be getting a list of services based on that label or based on the selector rather than the specific service name. Did I answer all your questions, or is there anything I missed? I think there was.
Partially, actually, because I wanted to understand, like, we do have Postgres implementation now running, which is we do use only replica while we have several container distributed within several GKA nodes, which are different from these ones. And basically, the order to containers which are located on the machines, they are constantly following the leader, and they do automatic switching, storing this information. I'm the leader, and I'm the other one, and I'm following the leader.
Sure.
I'm just storing this data next to the HTTP or using the DHCD. You're using the label for doing this, meaning that every time the container fails, you're going to runtime change this label for being able to the endpoint to understand that the other one fails and redirect the traffic through it.
That's essentially correct, yeah. So instead of asking for a specific service, you would just be asking for a list of services that follow a specific label or specific selector to follow who is the master. Different implementations have done that differently. For example, Patroni is a great product built by Zalando up in Germany. Great tool, really love it. This is just kind of a simple example for those that haven't worked with Kubernetes or Postgres. And then also, as I mentioned, CrunchyWatch and a few of those other tools handle that a little bit differently. So it really depends on your specific Kubernetes implementation.
That's good, thank you.
Yep. Any other questions? Yes?
How are you handling upgrades for the master primary?
Oh, so upgrading Postgres versions.
Yeah.
Okay. You've got a couple different versions. In the traditional world, you could run PG upgrade, which is a tool, which is a command line. So you could exec into the container and run PG upgrade. There's a fair amount of downtime with that. But then if we go back to the slides, there is a tool that we actually have. Oh, I apologize, that's a GKE window. I grabbed the wrong one. So if we take a look at here, we have Crunchy Upgrade, which allows you to do the major Postgres upgrades in place. We can go from 9.5 to 9.6, 9.6 to 10, etc. One thing, if you're not really involved in the Postgres world, it's a little bit confusing because prior to Postgres 10, the major versions were actually denoted by going from 9.5 to 9.6 was a major upgrade versus, like say, 9.5.8 to 9.6, or 9.5.9 was a minor version upgrade. With this last revision and release of Postgres, Postgres 10 is now the major version. Minor versions are 10.1, and the current version is 10.2, I believe. I think 10.3 may have been announcing. I don't know if that's generally available or not. So we have a container tool that will handle that for you. But then there's just a little bit of that clarification with the major versus minor version, how they changed that recently. Yes?
Still talking about upgrades, do you have any plan to use a logical application so that you can replicate to a newer version of Postgres without upgrading the engine? Any plan, any proof of concept, did you try it?
Yeah, that's actually, Logical is something that we've used definitely in-house. I believe that's something that we're currently looking at for the Crunchy Container Suite. I don't believe that's currently available yet, but it's definitely on our radar. So the difference with streaming replication is it's literally a binary copy of a pod versus the other, versus PG Logical allows you to replicate specific tables, namespaces, databases, etc. So that's a fantastic tool if you wanted to segment individual parts of the database out to a different pod for BI or analytics, or you could do the replication that way as well. We just haven't incorporated that into the container suite. All right.
Okay.
All right.